Good evening, everyone, and welcome to the University of Toronto. My name is Erin. I'm a fourth-year student at the University of Toronto, finishing up a double major in linguistics and drama. I just finished my very last undergraduate exam yesterday, and I am so excited to be graduating this June. Before we begin, I do want to acknowledge the land on which this university operates on. For thousands of years, this has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of this credit. We are so grateful to have the opportunity to work, study, teach, and learn on this land today. This meeting place is still home to thousands of Indigenous peoples from all across Turtle Island. Thank you for joining us for such a rare and wonderful opportunity to hear directly from a Nobel laureate, University Professor Emeritus Geoffrey Hinton, winner of the 2024 Nobel Prize in Physics. Professor Hinton is affectionately known as the godfather of AI. His research in artificial neural networks and deep learning have shaped the technology behind everything from the phones in our pocket to some of the most powerful supercomputers. His work has quite literally changed the way in which we understand thinking and learning. Professor Hinton is also deeply admired for his global advocacy for the safe, ethical, and responsible use and development of AI. He will be interviewed by Professor Melanie Wooden, currently Dean of the Faculty of Arts and Science, and the person who will become U of T's next president beginning this July. Dean Wooden is a neuroscientist who studies the mechanisms underlying learning and memory in the brain. Her work explores how neurons communicate and process information and how changes in this activity can lead to neurological disorders and diseases. And while we have two research powerhouses in our midst, you may feel reassured to know that when they first started university, they weren't 100% sure of what they wanted to study, or where their paths would take them even. This is just one of the many themes that we'll be exploring tonight. You might have also picked up on the fact that in each of their own ways, both Professor Hinton and Dean Wooden study learning. That's why a key focus of today's talk will be focused on honing your intellectual curiosity and your academic passion, finding the inspiration and confidence to dream big, how to be successful in research, school, science, and life, and so much more. Before I hand things over, I do have a few housekeeping things to cover. To ensure that you have an optimal viewing experience, please turn up your sound and minimize any windows that you have open. If you'd like to watch this event in full screen, please click on the little box located in the bottom right of your viewing screen. Our panelists will speak for around 25 minutes, following which we will open things up for a 25-minute Q&A for the audience, which I will be moderating. We'll be sharing instructions on the screen to tell you how to submit your questions. You'll see the prompts on the bottom of your screen appear occasionally throughout the session, so feel free to send in your questions at any point throughout the talk. In order to get through as many questions as possible, I will be reading them on your behalf, and we'll be grouping similar questions into general themes. We'll have people from every corner of the world joining us for this talk tonight, with over 1,600 students registered thus far. I'm also sending a big shout out to everybody coming in from Singapore, Hong Kong, and Beijing, all places where I personally grew up. All of you have been invited to this event here because you have received an offer of admission from the University of Toronto across multiple fields of study, from engineering to kinesiology, from music to math, from politics to architecture. As Canada's flagship university and one of the world's leading research institutions, that is no small feat. Congratulations. We hope that our talk today will give you a small taste of what our amazing learning community is about. Finally, let me comment very briefly about the beautiful space that we are in tonight. We are coming to you from a place called Hart House, a true gem on this campus. No matter what program you're in or which campus you're from, Hart House is open to you. Hart House is a historic, dynamic, and inclusive place where you can experience university life outside of the classroom. From debate clubs to theater groups and fitness classes, it's where you can meet new friends and mentors, discover what moves you, and just feel at home on campus. There's truly something here for everyone. All right, we are now ready for the main event, so sit back as we begin this highly anticipated conversation. Dean Wooden, please allow me to turn things over to you.
Thank you, Erin, for that kind introduction, and welcome everyone to the University of Toronto. I feel confident in saying that we are in for a very special treat. Over the last 5 years, Professor Hinton has provided me with much wise counsel. His dedication to science and scholarship, his mentorship, and his friendship have been immeasurable. And I hope that you'll get a sense of that too over the course of the next hour that we'll spend together. Now, we've got a lot of ground to cover, so let's jump right in. Professor Hinton, as you know, our audience is made up of students who are about to embark on their undergraduate career. And when I think back to being in at the point in their career that they're in, I was excited to come to U of T to study biology, but I also wondered if I'd picked the right subject and how would I know? So can you start by telling us a little bit about your academic journey and what your first year was like?
So I went to Cambridge. It was the first time I'd lived away from home. It was the first time I'd been a place where I wasn't one of the more intelligent ones. Everybody was smart there. And I found it very difficult, and I left after a month. And I went and did odd jobs in London, and I reapplied to do architecture. I got in to do architecture, and then after a day I changed my mind and went back to doing science. So it was fairly chaotic, my start at university. And if your start at university is chaotic, don't worry.
Well, I couldn't agree with you more, and that's one of the things that we really pride ourselves on at the University of Toronto is you know that when you come, you can take a wide range of courses and really explore your opportunities. So tell us a little bit more about what you then did study as an undergraduate student.
So in my first year, I did physics and physiology and chemistry. I did very well in physics, but I couldn't deal with the math. The math was too complicated. I could do intuitive physics, but I just found math very difficult. And so I decided I'd never be a physicist. And luckily, I quit physics, because if I hadn't done that, I would never have got a Nobel Prize in it. My math wasn't good enough. And the physiology I loved. I wanted to understand how the mind worked. But I was very disappointed in the summer term when they were going to explain the central nervous system. And they explained how impulses traveled along nerve fibers, but not how it worked. And so I switched to philosophy, because I thought philosophy might teach me about the mind. I was mistaken. So I switched to psychology. I thought that might teach me about the mind. And it taught me some things about the mind, but not how it worked. And I always believed that we had to understand how the brain worked to understand how the mind works. And psychology didn't teach me that. So then I became a carpenter. And a couple of years later, I decided I was going to go back and do graduate work. And maybe AI would be the place I would understand how the mind worked, because they could actually build things. We could simulate things on computers, so we could actually build little minds. And I still think that's a very good way of trying to understand how the mind works.
Okay, so a fascinating story because you tried out so many different disciplines and you were clearly driven by a quest for understanding a bigger problem, and then you began your graduate studies. Once you started those, did you feel that you'd really honed in on the specialty that would be your career?
Yes, after I started doing AI, from then on, I never sort of thought I should be doing something else. But I thought they were doing AI all wrong. So most people in AI believed that the most important thing about intelligence is reasoning, and reasoning must be done like logic. You have to have kind of symbolic expressions in your head, and you have to manipulate them using rules, and that must be how it works. And they were so confident, they couldn't really think about any other alternative. A few people understood that to understand the mind and the brain, you really had to understand how networks of neurons learn to change the connection strengths between neurons. But among those few people was Turing and von Neumann. Unfortunately, they both died very young.
So just coming back for a minute to the varied path you took in your undergraduate days, studying a number of disciplines and trying to find your path. If you had to do it all over again, would you still follow that path? Because I get the sense that it probably really helped you get to where you wanted to be.
So retrospectively, although it seemed completely chaotic at the time, doing physics and physiology and philosophy and psychology was all good background for what I did. So it sort of made sense retrospectively, but at the time it just seemed like chaos.
Well, as you'll know, having been a professor for many years, many students take a path that they may feel is chaotic, but as we know, often is the best path for them to get them where they want to go. there are a lot of accomplished academics in your family tree, yet you were able to step out of their shadows and find your own path, right? This passion that we're talking about. Can you give some advice to undergraduates who are thinking about how they find their own academic path? How do they have the confidence to do that?
I think you have to have something you're really curious about. So a lot of undergraduates sort of decide what subject they want to do. But with me, there was a particular problem I was interested in, which is how does the brain work? And once you've got a problem like that, that's what drives you. So it makes life much easier if you've got a problem like that. You just do whatever you need to do to figure it out. And for me, it was lots of different subjects I did. But I was always motivated by trying to understand how the brain works.
Okay, great advice. I've spoken publicly about my undergraduate days, how some of my most memorable experiences were ones where I could be found in the lab with classmates, often on a Friday night, and it conjures up a big nerd image for some people, but when I think back to it, this is when I was often most happy, my most memorable moments on campus. Can you tell us some of your most memorable moments as an undergraduate student? Or as a student in general?
So one memorable moment was when I was doing psychology. We had to do an experiment. It's one of the few experiments I've done. And the experiment I chose to do was trying to decide whether as children got older, they paid more attention to shape and less attention to things like color and texture. And so the way the experiment works is you take children between the ages of 3 and 5, and you teach them to do an odd one out task. So you show them 2 red squares and a red circle, and they have to point at the odd one out, and they quite quickly get the idea. And you show them, I'm going to get this wrong, 2 red circles and, 2 red circles and a yellow circle versus, for example, 2 red circles and a red square. So one's different on shape and one's different on color. Right. And they quickly get the idea that sometimes they're different on shape, sometimes they're different on color, and you have to point at the odd one out. And then you show them, and I'll probably get this wrong, a red circle, a yellow circle, and a yellow square. So now, the odd one out is either the red circle if you use color or the yellow square if you use shape. And this experiment was going okay, and I was getting the results I was meant to get, the very boring results, that as they get older, people are more likely to pick the odd one out based on shape than on color. And then one bright 5-year-old looked at the first test example. So he'd learned to pick the odd one out, and he looked at this red circle, and yellow square, and he pointed at the red circle and said, "You painted that one the wrong color." So now, this was a really dumb theory I was trying to support, that you pay less attention to color and more attention to shape as you get older. This kid understood what was going on. He understood it was an experiment. He understood that I constructed these things. He understood the idea of an odd one out. And he just thought I'd made a mistake because this didn't fit in with the training. And I'd probably painted the red circle red instead of yellow because I made a mistake. And at that point I thought, we're not really going to understand how people work until we can have a model where you train it like this, and then it behaves like this kid did. Instead of pointing at either the red circle or the yellow square, it says, hey, you painted the red circle the wrong color. Or at least it says, there's something problematic here, And that was 1970, so that was 55 years ago. And in the 55 years that have passed, we now have something that might actually be able to do that. If you take a large language model and you tell it this task and give it some examples, and then it needs to be multimodal, and you then show it this conflicting one, it might actually respond saying you painted the red one the wrong color. So we've come far enough that this idea I had at the time, which is psychology is completely hopeless because it can't explain why the kid would say that. Now we've got to the point where we might be able to do that. But it took 55 years.
Did you think it would take 55 years?
No. In fact, when I went to graduate school, my project for my thesis was going to be called Ludwig, after Ludwig Wittgenstein. And Ludwig stood for Language Understanding Device Without Innate Grammar, because I thought what Chomsky was saying was rubbish, and we ought to be able to learn language, And now we can do that. These large language models do that, but that took 50 years.
So many people, myself included, as you know, really look up to you as an inspirational mind. And you know, when you received the Nobel Prize, the impact of your work was compared to the Industrial Revolution and the discovery of fire, right? So I
should emphasize at this point, it's not just my work. There's a whole bunch of us.
Yes, yeah, very good point, of course. And so this really, what I'm trying to get to, somewhat what you've just touched on, are these seminal moments in your studies where you really had a passion for a research question. As you described to us, you had this curiosity about how the brain works. You just gave us a great example of an engagement you had in your undergraduate days where you really sort of sharpened the understanding of what we needed to do. But let's take it back a little bit further, maybe in your elementary school days or even sooner. Was there a time when you really realized that your curiosity-driven mind was leading you to a path of discovery?
I remember very early on seeing something impossible and being obsessed with it for a while. So I was coming home from school at the age of about 5. It was in a bus, and the seats sloped upwards towards the front and were covered in a sort of a coarse velvety material with sort of stiff bristles in it. And I put a big old English penny down on the seat next to me, and it traveled uphill. And I thought, that's not possible. So I put it down again, traveled uphill. Now, of course, I don't really remember in detail what happened then. I really remember I'm remembering it many times. But it traveled uphill, and that wasn't possible. And I puzzled about that for a long time. When I was older, probably when I was a teenager, I eventually realized what was happening was the engine of the bus wasn't well mounted, and the whole bus was vibrating. And so the bristles of the velvet were kind of like this, and the penny, when it went uphill, went this way on the bristles. So the engine made it vibrate like this. When it went this way, it could go. When it went this way, it was like a ratchet, it couldn't go. So the energy was coming from the vibrations caused by the engine. And the reason it went uphill was because of the slope of the fibers of the velvet. But seeing something just go uphill by itself, I was always really fascinated by things that were impossible.
So I will say that, in the first question, the answer that you provided, you said you didn't have enough mathematics to study physics, and made a joke about winning a Nobel Prize in physics. But it sounds like to me, when you were on this bus, you were already looking at physics problems. And
yes, I always loved intuitive physics. I was always fascinated by physics.
Yeah, so
it was just these big equations.
So, as a follow-up question on inspiration, did you have any posters on your dorm wall that you looked to for inspiration, or any other forms of entertainment? What were they?
At the risk of sounding extremely nerdy, my father was a biologist, and when I was a teenager, when I was about 14, he thought it'd be a good idea for me to become a biochemist. And so actually on my bedroom wall, I had a big diagram of the Krebs cycle.
Well, that clearly was good inspiration for future studies.
Maybe. I can't remember anything about the Krebs cycle except it takes everything down to pyruvic acid.
Well, that's a salient feature, so that's fine. Let's talk a little bit about motivation. We all face setbacks, right? Yeah. In our personal lives, professional lives, or when we're undergraduate students at every stage. Can you tell us what you'd say to a student who experiences a big failure or a setback?
It's not the end of the world. When you're young, you haven't had that much experience, and you can recover from big setbacks. I think, for me, I always had this motivating question of how does the brain work? And I got very fed up with psychology and did very badly in psychology. I went off and became a carpenter and decided I wasn't going to do academic stuff anymore. And then I met a real carpenter who was just much, much better at carpentry. And I decided actually being an academic was easier than being a carpenter. So I went back into academia. I think as long as you follow your curiosity, you're going to be fine.
Okay, good. I want to pick up on the curiosity a bit because you talked about your curiosity. We talked about the penny moving on the seat in the bus, and you talked about your curiosity about how the brain works. But I'm sure some members of our audience, and I know my own students, and whether they're in the undergraduate or graduate class, sometimes think, well, how am I going to think of these questions, right? And put too much effort into thinking about what is a good question to ask. So I wanted to dig down on that a little bit more. What advice would you give to people to thinking about great questions, and how do they find really their own curiosity?
I think they often start by just noticing something that seems a bit odd. And instead of just saying that's a bit odd, being interested in why it's a bit odd. So there's lots of everyday things that are a bit odd that most people never think about. For example, you go to the dentist, and the dentist says, bite down. And you just accept that. Actually, when you contract these muscles, your lower jaw comes up. So why does the dentist say bite down? Is he making a mistake? But all dentists make the same mistake. So what's going on? And if you ask dentists why they say that, they don't know, or they make something up. What's really going, and it took me a while to sort of figure out what's going on, which is when you think about the inside of your mouth, what's important is where your teeth are relative to your tongue. And if you ask which teeth are going to bite your tongue, well, your tongue is in your lower jaw. So your tongue comes up with your lower teeth. It doesn't move relative to your lower teeth. So it's the upper teeth that move relative to your tongue. So when you're thinking inside your mouth, then sort of you are your tongue, and it's the upper teeth that are moving, because your tongue's fixed to the lower jaw. So solving puzzles like that is what scientists love doing. That's just a little example of an everyday thing where most people don't get curious about the fact, why do they say bite down? Because it goes up. I can give you one other example.
Sure.
Very few biologists seem to be puzzled about a little piece of topology. So food goes in one opening and it comes out of another opening. Mm-hmm. The waste comes out of a different opening, right? Air comes in one opening and the carbon dioxide goes back out of the same opening. Well, that seems stupid. Why isn't it a straight-through system? And most biologists don't know the answer to that. They never even thought of that. But it's an obvious feature of us, and it's actually about not losing water vapor. So oxygen molecules are bigger than water molecules, and so any membrane that will let oxygen through one way will let water vapor through the other way. And so your lungs will let water vapor out of your blood, and you don't want to lose all that water vapor. So you have a long tube of mucous membrane, and as the dry air comes in, the wet mucous membrane humidifies it, and as the wet air goes out, it deposits moisture on the mucous membrane, and so by the time it gets out again, it's fairly dry. And if you look at a camel, it's got this very, very long tube. It's all wrapped up in its nose, so it doesn't lose any moisture. But that's an example of there's this obvious thing about our bodies, that the topology of breathing and the topology of digestion are different, but most people never sort of say, why is that?
So two great examples, and maybe I'll just add to that to say to the students that are watching, one of the things that we really encourage you to do wherever you end up pursuing your studies is to question not only the world around you, but everything you're learning in your classroom and what you're reading. Something may be presented as fact. Ask why that is. Where did this come from? You may be in the humanities. Dig into the stacks and libraries and find those original sources and read them. And I think what you're somewhat alluding to is you'll discover that there are a lot of unknowns behind what we think we do know.
Yeah, there's unknowns all around you.
Yeah.
It's just most people don't sort of bother to notice them.
Exactly. So even when your professors are going to tell you some knowns, they will actually be delighted if you question them on that, about the unknowns. And that's how you'll get into
the good ones will.
Yeah, we have good ones here.
Okay.
Let's fast forward a few years to your later years. It's, of course, tempting to think that your success came overnight. But in reality, most scholars in whatever discipline have dedicated a career, and as you described, with many of their colleagues, their students, trainees, over many decades, conducting what we call fundamental research or discovery-led scholarship into these unknown concepts. And when you embark on it, I don't expect you thought that you were going to change the world fundamentally. Let's talk a little bit about that. Tell us a little bit about when you were embarking on those questions. How much was it this curiosity-driven research, understanding how the brain works, or your considerations about how that could fundamentally change the world?
I guess the two went together because it was always obvious that if you could understand how the brain worked, you could make artificial brains that were as smart as us, and it would change the world.
Right. So one of the time points when I think it became clear to others that what you were doing was going to change the world, at least it became clear to computer scientists, was in 2012 when you won a fairly famous, now famous computer science competition run by a scholar, Fei-Fei Li, who had an ImageNet competition. And you went from being a highly regarded computer scientist and your colleagues to people realizing that things were fundamentally going to change. Can you tell us a little bit about how you felt at that time? Did that change things for you, or you already knew?
It was kind of vindication. We'd been saying for years and years that neural nets eventually are going to be able to recognize objects and images better than the standard method, which is to write programs to do it. Yeah. We don't know how we do it, but we can make something a bit like the brain that can learn, and maybe we can get a system that will learn to do it. And that's what we showed, that a system can learn to do it much better than anybody can program it. And so for years, people in computer vision have been saying, neural networks are nonsense. Some of their journals had a policy that if you submit a paper on neural networks, they won't even referee it because it's such nonsense. A few years later, they were all doing neural networks because we'd shown it really worked.
Right. Okay, maybe the final question, because then we want to turn it back to Erin to take questions from the audience. I've seen a lot of students taking selfies with you on campus. So this is a little bit about what's it like to win a Nobel Prize. Thousands of people dream about it. Of course, very few actually do. So do people recognize you on the street now, and how has it fundamentally changed your life?
Yeah, people do recognize me on the street, and a lot of them want selfies. And it's very annoying, and I'd probably be disappointed if it went away.
Well, that's a great way to turn things back over to you, Erin.
Great. Thank you so much, Professor Hinton and Dean Wooden, for such an open and honest conversation. If our audience was gathered here right now, I'm sure there'd be a standing ovation right about now. I'm graduating this June, and I wish I had heard this kind of advice when I was first starting my undergraduate degree. Now, that being said, I feel like a lot of what you just shared feels very relevant to me, not just for school, but for whatever comes next in my life as well. And I think I can speak for everybody watching as well when I say that we'll be carrying all of these insights that you've discussed for a long time to come. Now, let's get on with everybody's questions. Professor Hinton, could you talk a little bit about how you think science and the humanities work together and why this collaboration matters?
I think there's two interactions that are very important. The first is, as we develop new technologies, we need the humanities to make sure we consider how they affect people and people's lives. So that's one kind of interaction. The second kind of interaction is, as we develop more understanding of how the brain works, we're going to radically change our view of how people work, and that's going to change the humanities. We saw that once about 100 years ago. With the development of psychoanalysis, even though there was a lot of nonsense combined with some real insights, that changed the way people thought about people. We accepted that we have all sorts of unconscious motivations. We accepted that we use all sorts of analogies to do things rather than just reasoning. We basically accepted we were much less rational than we thought. This is an even bigger change that's going to happen, because up until now, most people, including in the humanities, have thought that we sort of reason using something like logic. We're rational beings. We're not. We're great big analogy machines. We work by seeing analogies. Analogies not just with one thing, but with lots of things. And so that changes what you think of as the nature of a person. We're analogy machines rather than reasoning machines. We've got a thin layer of reasoning on the top. And that's very important for doing things like mathematics. Without the reasoning on top, you couldn't have bank accounts and things. But we basically use analogies to think.
Thank you so much for your answer. That's really insightful. Another question that we have right now is, will artificial intelligence help with fighting climate change, or will AI make climate change worse?
Okay, in the short term, it might make it worse. People are busy trying to get all the electricity they can to train these great big chatbots, and they're significantly increasing the electricity consumption, so that makes climate change worse. But it'll also help us design much better materials, better solar panels, probably better wind turbines, maybe better nuclear power stations, much better materials for insulating buildings, maybe kinds of glass that can act as solar panels but be transparent, things like that. So certainly better batteries. And batteries are very important for things like solar power. So I think it's very hard to know right now, but in the short term it may be bad, but in the long term I think the benefits will outweigh that.
Thank you so much. Thank you for the comprehensive both short-term and long-term discussion as well. That's very interesting. Another question that we have also for you, Professor Hinton, is what is a scientific belief of or practice that you once held firmly but later changed your mind about, and what caused that shift in you?
Ooh. I can say a non-scientific belief.
Sure.
My father was a Stalinist, and I was raised to think that Joe Stalin was a good guy who saved Europe from Hitler. When I became a teenager, I became a bit suspicious of that. And I now don't believe that Joe Stalin was a good guy. I do believe that he helped save Europe from Hitler, but at a terrible price. And I didn't realize how terrible the price was until I had Ukrainian graduate students.
Thank you. And this is a question actually for both of you, Dean Wooden and Professor Hinton. What is a decision that you made early in your career that seemed small at the time, but had a huge impact on who you are and where you are right now?
Okay, it's a curious decision. I got into Cambridge, but I knew my math wasn't good enough. So I actually stayed at school for another 6 months and did more math courses. And I actually wanted to learn about probabilities. I don't really know why, I was just interested in them. And the math teacher said, well, he didn't know much about probabilities, but he had this little book on probability. And why didn't I, instead of doing the math lessons, why didn't I go to the library and read this little book and do the puzzles in the little book? And that made a huge difference in my career. Probabilities became something I kind of loved and felt okay with, and they wouldn't have been otherwise. So it was an insightful math teacher who realized I was really curious about probability, and rather than say, well, we don't teach that here, he said, well, go read a book about it.
Yeah, you know, I'm thinking a little bit about the students in our audience and remembering, you know, around the stage that they were at, getting a lot of advice from people, friends, family, whether you ask for it or not. And often people are giving you advice about the career path you should take, right? And part of that is often, you know, where are things going in the world? What is a good area of study, you know, for a future career prospect? And of course, thinking about the next steps in your career are important. But to be successful in any career that you're going to pursue really comes down to the passion that you have for it, right? You want to be fulfilled in whatever field you decide to pursue, whether you continue with studies or you go out into the workplace. So even when you come to university, you're going to be talking with your peers and maybe even advisors who might be talking a little bit about emerging industries. And it's important to consider those. And I had a lot of that advice, but I made a decision early on to really follow my passion, to really pursue questions that I was interested in. And even if I didn't have a specific question, an area of physiology or the brain that I wanted to learn more about. And by following that passion, you're going to be more successful, right, than following a path that someone tells you is going to have a positive outcome. So that doesn't mean that you can just go in a direction without thinking about the next step, but if you follow what you're excited about and you're interested in it, you're going to be the most successful, and that's going to set you up well to succeed in whatever next step you choose.
Thank you so much. On the topic on giving advice to students and also having teachers or professors that kind of aid you in your learning, another question I have from the audience is, what are some study techniques that you two have deemed effective throughout the years of your schooling?
So I think the study techniques depend very much on who you are. And I've noticed among scientists there's huge differences. So I don't like reading. I start reading something, and after I've read kind of one paragraph, I get distracted because it makes me think of something, and I start wondering about something. I'm very bad at reading scientific papers. I will read important papers in the end if I have to. I love talking to people. So I've got a friend called Terry Sinofsky who loves reading. He reads all the literature in neuroscience. And if I want to know something in neuroscience, I don't actually go and read a paper. I call up Terry, and he explains things to me, and that's much more fun. I guess in some ways I was fortunate to get the advisor for my PhD had the same kind of characteristic. And so he gave me advice early on. Don't read the literature. Reading rots the mind. First solve the problem yourself and then look in the literature to see if your solution is novel. Now, this is the exact opposite advice to what you'll get from almost all people. They'll say, you should read the literature, you should carefully, before you start on solving puzzles yourself, you should read the literature. I think both views are correct because it depends on who you are. Some people like reading a lot and acquiring lots of knowledge. Other people are puzzle solvers like me, and they don't like reading lots of stuff. They like a puzzle to solve. So I think there's huge variation in how you should study.
Yeah, I would agree that it really, your own learning style is going to be important. You're going to want to reflect on what worked well for you to get to this point. But one of the things that was my own experience, and I see time and time again with students, is that when they form study groups together, that's really valuable. And it might be because for some students, and I think we've heard from Professor Hinton, and I was certainly the same way, being able to discuss the concept, asking each other questions. I think most people will know that, you might think you understand a topic and then you try and explain it to someone and you realize, wait a minute, I think I'm missing something here. So it's a good way to really test your own knowledge, and maybe you did have a gap in your understanding, you now learned from someone else. But also, there's another value here, right? You're coming to university, you are outside of perhaps the smaller cohort of students that you had in your high school classroom. You're gonna meet a lot of other people, right? And you're probably gonna learn something together. It's probably gonna be a bit more fun if you're doing it together, and maybe afterwards you're gonna go out and have an ice cream or go for coffee or do whatever, or join each other and go to play a sport, right? So you're going to get a few other benefits if you get together with some other classmates and do it. And as you'll know, Erin, from your time, regardless of what program you're in, some students are going to do that naturally with others, but there's lots of great programs set up for that already that you can just join and meet others.
100%, I agree.
I'd like to add something to my answer. There's one particular person I love reading, and that's Darwin, particularly The Voyage of the Beagle. Because he's so curious about the world. And he was very interested in geology, but also in animals, obviously, and in the relation between the two. So he has wonderful observations there. Like he saw coral islands, and a sort of standard coral island has a kind of island and then a ring of coral around it. But there's some coral islands where the coral is like a mile offshore, and the coral that's living is on top of a huge pyramid of dead coral. And Darwin was very curious. How could that be? Because coral won't grow more than a couple of 100 feet deep. There's not enough light. So where did these huge pyramids of dead coral come from? And Darwin just did reasoning and said, well, it must have been that the whole ocean floor sank. And as the whole ocean floor sank, the coral kept growing to keep near the surface, but the island went down and got smaller, and the coral stayed the same size ring. And so eventually the coral was a long way away from the island. And it's full of stuff like that. And it's wonderful reading people like that.
Do you mind just reminding me what that book is called?
Sorry?
Do you mind just reminding me what that book was called?
It's called The Voyage of the Beagle.
Voyage of the Beagle. Thank you. I'm going to have to check that out later on. All right, another question. This is specifically for you, Professor Hinton. Should someone major in math or computer science if they want to pursue a career in artificial intelligence and machine learning? I know that you've talked a little bit about your experience, but do you think that that foundation in just math and computer science is still valuable or necessary even?
I think it's valuable. I think you should do as much math as you can stomach when you're young. It's difficult to absorb abstract mathematical ideas. You do it much better when you're young. So you should do as much as you can bear. But I've also noticed that students who just do computer science or just math and computer science don't have the same kind of curiosity about how the mind works as students who do cognitive science. The best students are the ones who do cognitive science and can do math as well and can program as well. So I think you should do a bunch of different things.
Yeah, all right, thank you so much. This is another question for both of you. How do you determine which opportunities you choose to pursue? It's a loaded
Well, right now, I just say no to everything because there's too many opportunities. There's just many too many. I think, looking back on my career, there was a period in Canada when if you wanted to get funding, you had to get funding from industry. And industry would fund you to do research that can lead to immediate payoffs for particular companies. And I think it was a big mistake to take that funding. I think that funding actually set back science. It was much better to take less money and do basic research on the questions you're really interested in and not be distracted by trying to do things with quick payoffs.
Yeah, maybe I think about the question a little bit. Maybe I'll put it to thinking back to my time as a student for our audience tonight. I think they should be really open to a lot of opportunities. Again, you come in thinking there's something particular you want to study, or maybe in a particular club you're interested in. But maybe you're in a study group, and as I said, one of the members says, "Hey, I'm going to go and go see a play tonight. I'm going to go to Heart House, to the music room. I'm going to go to the debate club." And maybe these aren't things that you ever pursued before, but I'd say take that opportunity and go, right? Because your time at university is really a time to grow your mind, try new things, meet new people, and you're going to be able to do that when you say yes to those opportunities.
I love that answer. Thank you so much, Dean Wooden. This is another question for the two of you again, but how can somebody figure out what they're truly passionate about, especially if, like in your case, you tried a ton of different things out and you're passionate about so many things all at once?
I think if you have to figure it out, you're not really passionate about it. For me, understanding how the brain works from about the age of 16 was the thing I wanted to do most. It's still the thing we still don't understand. I'd still like to understand how the brain works. We've produced a lot of technology in our attempts to understand how the brain works, but we haven't figured out how the brain works. We know a lot more than we did, but we still don't really know. Somehow I think if you have a real passion, you know about it.
Yeah, I would say that, the subjects that students study in high school are relatively limited. And that can be for good reason. But what a lot of students come to learn, and Erin, I expect this might be similar for you. You did a double major, and many of our students now do a variety of different programs, is you come in and you have access to courses that are in disciplines you didn't even know existed. So we really just encourage students to, read through the calendar, say, well, that looks interesting. I wonder what that's about, right? And take a really wide variety of courses in your first year, because chances are you're going to find your passion for something. It might not, and it might not quite right away. You might say, wow, what is this field of study about? I'm going to take another course and find out, right? So really pursue a range of courses, again, things that you might have never thought that you would have been interested in, and I'll come back to that point. You might not know where they're going to go, but that's okay. And also, your passion might not end up being in a particular disciplinary subject. Your passion might come from engaging, as we just talked about, at Heart House or anywhere else on one of our 3 campuses, where you get really excited about something. Maybe you join the student newspaper or your student government, and you realize that you've got a passion for that. So you can find it in a whole variety of places.
Yes, I love that concept of trying many things out and slowly discovering what you're really interested in, whether that's how the brain works or anything else. I know when I was in my first year, I didn't know what linguistics was, and I had to discover it in my second semester before being like, oh my gosh, this is what I want to do. That's so interesting. Thank you two for your answers. Another question I have for Professor Hinton right now is, what do you believe is the potential of AI in the future in terms of the healthcare system itself?
Oh, I think it's tremendous. So I did make a prediction in about 2016 that within 5 years or so, I can't remember what the prediction was, maybe within 10 years, we wouldn't need radiologists to interpret scans. That was a bit optimistic. We still need radiologists to interpret scans, but now AI systems on many kinds of medical image are about as good as doctors, as radiologists, and they're getting better all the time. So a radiologist can't look at 1 billion images. But if you take chest x-rays, for example, there's 7 billion of those that were done on the web. And you can train an AI system now on 7 billion chest x-rays, and it can be very good at diagnosing all sorts of things from those. Or skin cancers and things. AI systems are comparable with dermatologists now, and possibly better already, at looking at something on your skin and saying, could that be a melanoma? So they'll be very good there. But they'll also be very good as family doctors. So you go to your family doctor now with some rare disease, which your family doctor's probably never seen before, maybe read about if you're lucky. And doctors make a lot of mistakes in diagnosing things. In America, about 200,000 people a year die from a bad diagnosis from doctors. Already last year, if you took difficult diagnostic problems, if you compared, like the kind you get in-house, but maybe not that crazy, if you compare a doctor, the doctor was getting 40% of them right, an AI system was getting 50% of them right, and the combination of the doctor and AI system was getting 60% of them right. Well, that's already a third of the errors in diagnosis gone away from last year's AI. And as you know, AI is getting better very fast. So AI is going to be much better at diagnosis. It's going to help us design new drugs. The work done at DeepMind on how proteins fold is going to be very useful in understanding how to design new drugs. And they've got a whole new team set up to do that. So I think it's going to make a tremendous difference in the quality of healthcare you get. The other thing about healthcare is, you realize this when you're old, there's no limit to how much healthcare you can absorb. Old people would like to have several doctors belonging just to them to ask questions of. So it's not going to put people out of work. If you have AI that does very good diagnosis and very good interpretation of images, you'll just get a lot more healthcare. Other areas are different. AI may put people out of work, but in healthcare, there's room to absorb hugely more healthcare.
So interesting. So specifically in like the diagnosis and detecting area, do you think there might be any more advances in, let's say, surgery or any other areas in healthcare as well?
Oh yes, there's both the diagnosing what needs surgery, but actually doing the surgery. They already have robots that can do surgery, and those are going to get better. Now, I'm a bit wary about giving a time scale. My guess is in 10 years' time, there'll be quite a lot of robots doing surgery, but it might be 20.
Okay, very interesting. This is another question for both of you, and you touched on it a little bit, Professor Hinton. Like you mentioned, a lot of the times people will face setbacks both in their personal life, in academics, and their professional life as well. But could you talk a little bit about how you deal with failure? Whether do you reframe it or avoid it, or do you kind of embrace it and kind of twist it in a way? Yeah.
I think different people deal with failure in different ways. There's probably many different ways to deal with it. I'm not an expert on how to deal with failure. I remember when I quit psychology because I thought it was useless and became a carpenter, I remember at one point I went to an encounter group. This was the 1970s. Life was different then. We had groups where you would get together and spend a weekend together with other people talking about your fears and your hopes. And right at the end, people had to say what they had to sort of shout out as loud as they can what they really wanted. And most people shout out things like, I want to be loved. That's the sort of general thing. That's what you sort of expect to shout out. And I found myself shouting out, I want to get a PhD. So then that's what I really wanted. It wasn't particularly acceptable in that circle for that to be what you really wanted, but there you go.
Yeah, I mean, I think picking up on what Professor Hinton said at the beginning, you know, people are going to manage it in different ways, but it's a good question to ask because, as we talked about earlier, you are going to experience setbacks, personally, professionally, at every stage of your career. And when you embark on your university career, you may be moving to a new city. It might be the first time away from home. As we've heard from Professor Hinton, you're going to realize there's a lot of other smart people beside you. Chances are things are not going to go maybe as well as you had hoped, right? So you want to think in advance about how you're going to manage that, right? What are the things that you know are good for you to do to stay mentally well? So, you know, in my own case, I love to long distance cycle and hike. And so I know that, you know what, if I've had a setback, I'm upset about something, a good thing to do is actually to get outside and spend some time outside and, you know, get your endorphins up. But then the next thing that is also good to do is to talk to someone about it, right? And sometimes that is me talking to another professional colleague, kind of talking through a difficult situation, you know, how have they dealt with it, you know, playing devil's advocate and getting their advice. And sometimes you need someone who's a professional, and Professor Hinton referenced that as well, right? They're professionals, so, you know, it's good to use those resources, whether it's an academic advisor that can say, you know what, I see this a lot, this is, you know, this is normal, this is how we support students through it, or accessing more specialized care. But we need you to tell us that you've had a setback so we can help you.
Totally. Thank you so much for both of your answers. And this is another question for both of you again, but during both of your times as students, were there any specific extracurricular activities or hobbies that the two of you were especially passionate about?
I've always loved carpentry, and when I was at high school, the class I liked most wasn't math or physics or any of those classes, it was carpentry. It was voluntary and you could do it in the evening, but I just loved it. You're actually making things.
What's the coolest thing you've made so far?
I made some shelves at home, a big storage unit that was made with no screws or nails, by taking pieces of wood and laying them out and putting glue on them and sticking other pieces of wood on. And I made big frames that could support shelves. That's probably one of the biggest projects I've done, and that was a lot of fun. It wasn't joinery, didn't look nice, but it was very functional.
So you know, when I talked about spending some time, maybe on a Friday night in the lab, with these other students, and a group of the students said, oh, you should sign up with us to play intramural inner tube water polo.
Yeah.
And I said I'd never played water polo, and they said it really didn't matter. And so I went, and I ended up playing intramural inner tube water polo for several years, and it was one of the most fun activities I have ever played. I've never played again, and it turned out I'm terrible at catching a ball or throwing a ball. Intramural water polo is mostly just about trying to tip other people out of the inner tube. So you never know what kind of fun you're gonna have.
Oh my gosh, I love that. I actually did that in my very first semester at U of T as well. Intramurals for Victoria College. All right, this is another question for both of you again, but the student wishes to pursue a career in academia as a professor. So what's the most important thing that the student should keep in mind as they go about their journey and in achieving this goal?
I'll give you one curious piece of advice that I got from one of my students. So I had this student apply to work with me, and I asked, why did you apply to Toronto? He's applying as a graduate student to do a PhD, but if you want to be a professor, you probably have to get a PhD first. And he said, well, I looked at the various places I might go to work on neural networks, and I looked at what your former students are doing. And most of your former students are professors. So I applied to you because you've got a very good record of your students turning into professors. That's just a little piece of advice. When you do your PhD, just check out how many professors your proposed PhD advisor has produced. Now, it's not necessarily the best thing to do because you'd also like a young professor who can give you lots of time.
So, you know, when I came to university, I wanted to be a scientist. but I didn't actually know where scientists worked, right? I'd actually come across some, I think they were probably U of T graduate students in Northern Ontario collecting some water samples when I was camping one time. And I asked them what they were doing, and they said they were doing a science experiment. They were from the University of Toronto. So I said, oh, I'm going to go to the University of Toronto then to be a science student. So I actually came here thinking I would study ecology because I thought that's how you could be a scientist. I didn't even know that where the vast majority of science and or scholarship research is done is by professors at universities. So I'm just sharing that because other members of the audience might be wondering what really is involved in being a professor, right? And it's about a commitment to excellence in research, and it can be in any type of scholarship. Or two scientists here, but it could be in linguistics, engineering, nursing. You can think about all sorts of disciplines. So first of all, you can come here to pursue that knowing you want to be a professor. You might come here not even knowing that's a path, but discover it when you get here. But really, it's about an interest in the quest for new knowledge. And so coming with that very open mind and seeking opportunities to engage in scholarship. And I use that term to say both scientific experimentation, but also scholarship with historians, political scientists, creative writers, all across our disciplines. Really look for opportunities that you can have to work with those professors, because that's how you're going to get some opportunities to understand what that type of career is like.
Thank you. Could you actually talk a little bit about your journey to where you are now, like into professorhood?
Yeah, sure, professorship. So I did come interested, as I said, in being a scientist, and it was actually in one of my first year classes where a professor explained that if you wanted to become a professor, you would do your undergraduate degree, and then you would do your master's degree, and then you would do your PhD, and then you might even do something called a postdoctoral fellowship, and then you could become a professor. And my friend and I were in the third row in Convocation Hall, and we started snickering, and we were kind of like elbowing each other, because I thought, who would do that? I thought, that's so much school. But what, of course, I came to learn is that, as I got more interested in research and wanting to pursue this as a career, that when you move to those next stages, a master's or a PhD, you don't necessarily do both, and you don't always need a postdoctoral fellowship depending on the field. But what you're really doing in that degree is you are, in fact, almost like a medical resident, right? You are engaging in that scholarship, such as what a professor would do. So you are still learning, but you are also practicing. So it's not what you're going to experience as an undergraduate student. You've got the course load, you've got the exams. So I did get excited. I was no longer worried about doing all of that school because I realized actually that's the start of my career. So I did do a master's degree and a PhD, but actually I was changing my path, not as much as we heard about Professor Hinton's undergraduate, but I started first in ecology and evolutionary biology. I got more interested in physiology and respiratory physiology. That led me to neuroscience, and I shifted all of those sort of disciplines from my undergraduate to my PhD and postdoctoral fellowship. And then, in fact, back in my home department here at U of T, a position came available, and I came back to start my lab here full circle.
Wow, oh my gosh, what a journey for you too. All right, our very last question is just for you, Professor Hinton, but what advice do you have for students like me who dream of contributing to science in a meaningful way, maybe even winning a Nobel Prize one day?
So I guess my advice is really original ideas come from noticing that people are doing things wrong, or that you think people are doing things wrong. So everybody's doing something one way and it doesn't feel quite right to you. And you sort of have a sense there's something not quite right here, and you focus in on that and try and figure out what's not quite right. It's a bit like when you read a detective story, somewhere in chapter 1, there's something that happens that when you read it doesn't feel quite right, but you ignore it. And then later it turns out that's the crucial thing, and that tells you who the villain was. And science is very like that. There's something that's just not quite right, and if you keep working on that, then maybe there's nothing there. but maybe that's the sort of thread that leads you to some really original idea. And until you've understood what's going on, you shouldn't give up on it. You should sort of focus. You should be like a sort of terrier. Once you've got that thread, you just work on it.
All right, thank you so much for this insightful advice. I'm afraid that's all the time that we have today, but an hour definitely flies by when you're having a conversation this intriguing and thought-provoking. As we conclude our program, I would like to extend a special thanks to Professor Hinton and Dean Wooden. Professor Hinton, you are one of the greatest minds of the 21st century. You have made some monumental contributions to foundational science and world-changing innovation and to the ethical use of resulting technologies for the good of all of humanity. It's been a real privilege hearing from both of you directly, and it's definitely something that I will remember for a very long time to come. Thank you as well to everybody who's joined us tonight. No matter what part of the world you're in or what program you're interested in studying, we hope that you take some of this inspiration with you to wherever you're headed. We will be sending out a link to this recording of this talk if you would like to revisit any of it in the near future. Thank you again for allowing me to be your host. I wish you all an amazing year ahead and a very successful future wherever you may be headed. Goodbye, everybody.